Hello everyone, this is Kinjal Parmar. Today we will start unit number 4 A to D and D to A converter, in which we will discuss D to A converter. So let's start. D to A converter. A digital to analog converter, says DAC, converts a digital signal to an analog signal in form of voltage or current. Basically, digital to analog converter converts a digital signal into analog signal. A digital to analog converter takes a digital code as input and produced an analog voltage or current as its output. This analog output is proportional to the digital input. Here we have a basic block diagram of D to A converter. We have a digital inputs or says 4-bit binary pattern. We have a MSB, then 2 bits and then LSB. Now using this D to A converter, we can convert this digital input into analog output. That means we have a here analog voltage, and this binary patterns converted into this analog output voltage pattern. We have a various kind of digital patterns, right? For example, for a 4-bit we have a total 16 combination. So for each and every combination we have a different analog output voltage. So this is how we can convert these digital inputs into analog output. The digital to analog converter output voltage is a unique value. In general, analog output is equal to K into digital input. This K is a basically proportionally factor which is multiplied with the digital input to convert analog output. These two methods are used to convert digital value into analog output. We discussed about this method, but before that, let's discuss about specification of this D to A converter. Specification of D to A converter, that means what are the criteria which we have to consider when we design this D to A converter. So number 1, resolution. Resolution of D to A converter is defined as the smallest change that can occur in an analog output as a result of a change in the digital input. That means resolution of any D to A converter is defined as smallest change that occur when we change this digital input. Like for example, we have a 0 digital input and we have a 1 volt for that, and for 0 1, that means for 1 we have a 2 volt. So there is a difference between analog output when we change this digital input, right? So this difference of this analog output is known as a resolution. For example, for 0 we have a 1 volt, for 1 we have a 2 volt. So here we have a analog output difference 1 volt. So this 1 volt is known as a resolution of that converter. Okay, so resolution of a D to A converter is defined as the smallest change that can occur in an analog output as a result of a change in the digital input. The resolution is always equal to the weight of the LSB, and it is also referred as step size. Although resolution can be expressed as the amount of voltage or current per step, it is also useful to express as a percentage of full scale output. Now, what is full scale output? Full scale output means analog output when digital inputs all are 1. For example, we have a 4-bit digital to analog converter, then output, analog output related to 15. Why 15? Because in 15 we have a 1, 1, 1, 1, 4 times 1, right? So for 4-bit, if we have a 4 times 1 and we have a regarding output like 15 volt, then this is known as a full scale output. That means analog output when digital input all are 1. Okay, so we can express this resolution as a percentage of full scale output. So how we can calculate this resolution? So here we have an equation. Percentage of resolution is equal to step size upon full scale output cross 100%, because here we denote this in terms of percentage. Okay, we can also write this as a 1 upon number of total number of steps. Okay, 1 upon total number of steps. That means for 4 bit, like we take 10 steps, so here we can write this as a 10 step, then 16 steps. Number, whenever we have a number of steps large, then we have a smooth analog value. Okay, and this total number of steps in any n bit D2A converter is equals to 2 raised to n minus 1. So here we have an equation 1 upon 2 raised to n minus 1 into 100. So for any n bit, we can calculate percentage of resolution in terms of full scale output and step size. Basically, sometimes step size and resolutions same, but percentage of resolution is different. Okay. Then second term, accuracy. The accuracy of digital to analog converter is specified in terms of its full scale error and linearity error, which are the normally expressed as a percentage of full scale. Basically, full scale, that means full scale output. Now, what is full scale error and linearity error? So full scale error is the maximum deviation of D2A converter output from its expected value. Maximum deviation from its expected value, and linearity error is the maximum deviation of analog output from ideal output. Okay. Here in full scale we consider expected, and in linearity error we consider ideal. Okay, so here we have a, if there is a change in expected value and produced value, or says whenever change between ideal value and processed or says produced value, then there is a error. Okay, and according to the type of this difference, we have a two types of error: full scale error and linearity error. According to this error calculations, we can calculate accuracy for this D2A. Accuracy is a comparison of actual output with expected output. Okay, accuracy means a comparison of actual output voltage with expected output. Then third, settling time. The operating speed of a DAC is usually specified by giving its settling time, which is the time required for the DAC output goes from 0 to full scale, as the binary input is changed from zeros to all ones. So basically it is the time required for DAC for a producing output. When we have a 0, then we have a all 1. Okay, so there is a time difference between that, and this time is known as a settling time. Monotonicity. A DAC is said to be monotonic if its output increase as the binary input is incremented from one value to next. Whenever output increase for each and every binary, that means that D2A converter is a monotonic. Then fifth, offset voltage. Ideally, the output of a DAC will be 0 volt when the binary input is all zeros. In practice, however, there will be a small output change for this situation. This is called offset voltage. Ideally, the output of a DAC will be 0 volt when the binary input is all 0. Basically, for 0 input, we have to output 0. But in a real-time applications, we have a small output voltage. For this situation, this is called as a offset voltage, and this has to be corrected. Okay, this offset voltage, if not corrected, then will be added to the expected digital to analog converter output for all input cases. So we have to correct this 0 whenever we have a output for a 0 input condition. So here we have a total 5 specification of digital to analog converter. Now let's discuss about two types of method of digital to analog conversion. First, weighted resistor type D2A converter. In the weighted resistor type D2A converter, each digital level is converted into an equivalent analog voltage or current. Here we have a basic figure of this weighted resistor type D2A converter for 4-bit. Okay, in this circuit we use basically this operational amplifier. Here we have this is summing inverted operational amplifier. Why inverted? Because we give input in this condition. What this amplifier does, so working function of amplifier is to amplify the input signal, right? But here we use operational amplifier, and the operational amplifier basically performs here addition. Okay, according to these conditions we have a this operational amplifier perform adder circuit, and we have a addition of this input conditions by using this circuit. Okay, so here this circuit is a summer operational amplifier. Summer, that means operational amplifier which performs the sum operations. And here we have a two condition, that inverted and non-inverted. Here we give input in a inverted, so we have a gain which will be inverted, or says output which will be inverted. Okay, now here in D3 says for MSB we use R. For D2 we have a 2R, then for D1 we have a 4R, then for D0 we have a 8R. Basically for D0 we have a 2 raised to 3 into R. Why 2 raised to 3? Because here we consider n is equals to 4. N is equals to 4. So according to that, here we have a resistor of 2 raised to 0 into R. Here we have a resistor 2 raised to 1 into R. Then we have a 2 raised to 2 into R. And here we have a 2 raised to 3 into R. For n bit, we have a last resistor weight 2 raised to n minus 1 into R. Okay, so this is how this circuit digital to analog conversion take place in weighted resistor type. Now how this binary pattern converted into this? So first here we have a D3 and we have a R. So here voltage is equals to D3 divided by R. Now here we consider a feedback resistor RF, and after this we have basically operational amplifier amplifies the signal, and to amplify the signal we have a here feedback resistor, and as we can give this in a inverted, so we have a minus RF into D3 by R. And like this we have a different bits. For example D3, D2, D1, D0. So we can write minus RF D2 divided by 2R, because here we have a 2R. Okay, so for D2 we can write over here 2R. Then for D1 we can write RF D1 divided by 4R. Then minus RF D0 divided by 8R. So this is how we have a analog voltage over here, and we have to add this all the voltage for producing a output, and we can write this as a simplified equations over here. We can take a common this minus sign and RF by R. So we have a equation D3 plus D2 plus D2 divided by 2 plus D1 divided by 4 plus D0 divided by 8. So this is how we convert this bits of digital into analog voltage. For example, if we have a pattern like 1 0 1 1, and like if logic 1 is equals to 5 volt, so we have an analog voltage for this 1011 pattern is D3 1, that means 5 volt. Then D2 zeros, that means 0. Then D1 1, so we have a 5 divided by 4. Then D01, so we can write this as a 5 because we have a logic 1 is equals to 5 volt divided by 8. And for example, RF and R both are equal. So RF and R cancel out. So by solving this, we have a analog output voltage for particular this 1011 application. Okay, for this 1011 binary pattern. If in example you have a question like calculate full scale output voltage for this, so for full scale you have to consider all digits are 1, so only change over here you have a one term added, 5 divided by 2. So by considering this, we can calculate full scale output for logic 1 is equals to 5 volt. Okay, here we consider logic 1 is equals to 5 volt, but in example maybe logic 1 is equal to different analog voltage. Okay, so we have to consider this. So this is how we can convert this binary pattern into this analog voltage using weighted resistor. By weighted resistor because here each and every resistor has a different weight. For example, for D3 we have a R, then for D2 we have a 2R, then for D1 we have a 4R, then for D0 we have a 8R. So this is how we can convert digital into analog output voltage using weighted resistor. Here is this weighted resistor. It consists of inverting summing operational amplifier, parallel binary weighted resistor bank, and a feedback resistor RF. The input resistor value are set to the multiples of 2, that is 1R, 2R, 4R and 8R. The output voltage would be equal to the sum of D3, D2 by 2, D1 by 4 and D0 by 8 according to the weight of this resistor, and then multiply with operational amplifier gain factor which is minus RF by R. This D3 correspond to the most significant bits while D0 correspond to the least significant bit. Here we have a equation V0 is equals to, as we discussed previously, we have a D0 is equals to minus D3 into RF divided by R, then minus D2 multiplied by RF divided by 2R, then minus D1 into RF divided by 4R and minus D0 into RF divided by 8R, and by taking minus sign and RF by R common, we have this logical expression for analog output voltage. So this is how we can convert digital to analog using weighted resistor type. But here, as the number of bits is increasing in the digital input voltage, the range of the resistor values become large and accordingly the accuracy becomes poor. In general, for n bit, B0 is equals to d raised to n minus 1 upon 2 raised to 0 plus d n minus 2 upon 2 raised to 1 plus so on, and last d1 2 raised to n minus 2, and for d0 we have a 2 raised to n minus 1 weight into RF by R. A different value resistor must be used for each bit position of digital input, and it is difficult to design more accurate resistor as the number of bits present in the digital input increases. So here we have a disadvantage of this weighted resistor type D2A converter. That means we have to use different resistor for different bits. If we have a n bit, then we have to use different values resistor of a n bits, or says for a n times. Okay, so it is difficult to design more accurate resistor as the number of bits present in the digital input increases. So we can use another type of D2A converter which is R2R, in which there are only two type of resistor, R and 2R. So that will be discussed in next session. Thank you.